All right. Good morning, ladies and gentlemen. Bringing in the online audience. 10:01. I'm a minute late. Apologies. Um, welcome back to your favorite class. Yes. All right. A couple of announcements, and I did kind of show these announcements in my lecture lobby here. Is that your homework number 1 was due today, maybe literally 10 seconds ago. So if you didn't get it in, too bad. So sad. Okay. Um, I usually try to turn around your homework's graded in about 24 hours, so you should probably see that, by the end of the day for me today. I'll post a solution. You can take a look at it. A lot of questions on this, especially related to directionality of the stresses. So um, I will spend a little more time over the coming slides talking about directionality of stresses because I think maybe I passed over that a little bit quickly in the beginning here. So we're all clear on that. But generally, I'll try to get comments back to you kind of as quick as I can. Also, you've all been through the lab at this point, and your first draft, or rough draft, whatever you want to call it, of your lab report is going to be due, as a reminder, 1 day before your normally scheduled lab. So those of you in the Tuesday lab do on Monday. Those of you in the Thursday lab will do on Wednesday. And the purpose there is I need 24 hours to sort of return it back to you. And then we're going to have individual one-on-one meetings next week during the lab period where I kind of meet with you virtually on Teams and talk about your writing and things you might do to improve your writing. Okay? If I don't get that rough draft from you 24 hours before that, I'm not going to have time to look at it, and you're going to miss a lot of valuable feedback. I'm really only going to go in super depth on your writing probably this one time this quarter. Okay? So this is like your one time to really get good, strong feedback about your technical writing. Might not be an opportunity you have in any other class going forward. So really, you should take advantage of this. Question? Yes. Okay. The question is, what is happening next lab report, and when is the final lab report due? So what's going to happen in lab next week is I'll send out a sign-up sheet for you guys to sign up for like 10-minute blocks of time. You'll sign up for a time, meet with me in Teams for 10 minutes. I'll kind of go over your writing with no grade attached. All right, it's just feedback for the sake of feedback for your learning process. Then 1 week from that day, which will be, not this upcoming Tuesday or Thursday, but 1 week from that, your final lab report will be due, and that's what I'm going to give you your grade on for this particular lab. Okay? All right, other questions? Okay. Uh, if there is no further ado, I hate ado, let us continue with the lecture material. So, let me get my writing pad up here, and I'll get rid of my quarantine day. God, what? Bill Murray, thank you. I was like blanking on his name for a minute. Mr. Bill Murray. And we'll sort of recap a little bit about where we left off. And we were talking, and this is going to be in the principal stress notes. So here we'll just do like a little recap of sort of what we talked about last time, and that is sort of an introduction to principal stresses by talking about stress at a point. So we sort of started the lecture, or sort of midway through the lecture last time, by sort of drawing like kind of a mechanics potato that was supposedly three-dimensional, even though my um, drawing skills suspicious. Imagine this is three-dimensional. And we drew like a series of forces on this guy, if you sort of remember this. And the idea here was we're motivating, all right, if we have some random point inside of this structure, let's call it just random point O, and we're interested in what is the full stress state, three-dimensional stress state at point O, we need to sort of cut through the structure and balance the forces to appropriately calculate things like the normal and shear stresses so that we can get the full state of stress. So we went through an example where we sort of like kind of cut through this guy in a plane that looked a little bit like this. Okay, and that would give us a cross section here in our cut through piece that contains point O and still has sort of like the remainder of the object on the backside here that still has some of these forces that are acting on it. And we're going to get resultant forces and moments in this particular cross section, just like you were doing for your homework. You're right, relocating the forces on the structure to give you equivalent reaction forces and reaction moments, right? And from that, we can then do calculations of the stresses on this particular cross section to get like normal and shear stresses. Okay, so then we end up calculating using your normal and shear stress equations for like transverse shear, torsion, axial stress, and bending to give you what would be stresses in this cross section, specifically at this point of interest, point O. So if we have some coordinate system here for this particular piece, which is like X, Y, Z, then we can begin to accurately define some of our three-dimensional states of stress with the cut that we have here. So here we've cut through what is the YZ plane. And this is at point O. And the result here is that we can determine the normal stress on this cross-section, which is coming off of the normal direction here. And for normal stress, we're going to obviously use the variable sigma. And this normal stress here is on the x face in the x direction. So we would denote the subscripts here as sigma xx, or a lot of times you'll just see it as just sigma x. All right. So as a reminder, when we're using the two subscripts on our stresses, we're sort of defining the face upon which it acts and the direction. All right. That is the normal stress coming off of this face. We also could potentially have a shear stress on the x face in the y direction and a shear stress on the x face in the z direction. So we could have tau x y and also a tau x z. Right? So by cutting my potato arbitrarily at point O along what is the YZ plane, I end up with three states of stress that I can sort of calculate using my combined loading strategy that we sort of talked about like in week number 1. Okay, and so we cut along the YZ plane at O, and we're going to get like sigma xx, tau xy, and tau xz. So you notice when I cut through the YZ plane, the stresses that I get all on the x face, and so the leading subscript is all x's in this particular situation. Right? Now, that is not the full picture of the stress state at O. I have to do more cuts to get the additional stresses, like the normal stress in the y direction or the normal stress in the z direction. Okay? So we need 3 orthogonal cuts to fully define the stress at O. So we need 2 more cuts, and I'll put this in quote, to give full stress state at O. Right? And so we might cut through, let's say, the XY plane. And have some picture that might look like this. We cut through the XY plane. We're kind of cutting across the face that we already see. Okay, so here's maybe my potato face, and we've cut through it so that we're sort of like cutting through in what is sort of this plane that is parallel to the page that we're looking at. And so here in the middle is again like your point O, and we'll keep the same coordinate system where we have like X, Y, and Z. And now if I cut through the XY plane, I have the Z face that is exposed, okay? And so if the Z face is exposed, then I can have my sigma Z, Z. Sorry, I just bad handwriting there. I'm gonna correct this. Sigma Z, Z, because it's on the Z face in the Z direction, right? So that's kind of the nomenclature that we're using. And also with this cut, we can define the shear stresses in the two directions, which would be on the Z face in the X direction and on the Z face in the Y direction. Okay, so here we have tau on the Z face in the X direction, and here we have tau on the Z face in the Y direction. Okay. Same idea if we go through what is the last plane that we need, which is the XZ cut. You might have your potato now looking like it just got its head lopped off. Just like 17th century France. All right? You got your head chopped off. All right, here's again our point O. And now it's the y direction that is the normal to the surface. So we can define sigma y y. We can define what is tau on the y face in the x direction. And we can define, this one's a little bit harder to draw, but here's another shear stress, tau on the y face in the z direction. All right? So each one of these individual cuts is giving us like 3 states of stress. All right, so here this is sigma zz, tau zx, and tau zy. Here's this sigma yy, tau yz, tau yx. All right, so the point is I need like 3 orthogonal cuts to really define all of the stress states. And I have 9 possible stress states that could exist at any particular point. And so we're kind of getting into new material now and saying that need 3 orthogonal cuts to fully define stress state. Okay? And we have 9 states of stress, the normal stresses, and all kind of 3 of these normal directions would be like sigma xx, sigma yy, or sigma zz. Man, my hand is like shaking. I had way too much coffee this morning. I had like a liter of coffee. It's like a liter of cola. All right. Anyone super troopers? No, super troopers. No. Okay. I want a liter of cola. All right. And then there's 6 shear stresses. All right. Looks like I might have a question in the chat here. We have a question. No question. Okay. The 6 shear stresses that you might have are tau xy, tau xz, tau yx, tau yz, tau zx, and tau zy. Right? Now, I'll just be very specifically clear here with the nomenclature. And I've sort of like alluded to this already, but I just want to make it crystal clear. All right. And that when we're talking about like, let's say a shear stress, we would have something like tau ij. The nomenclature is here that this is the shear stress that's acting on the I face in the j direction. All right. Now, maybe you learned this and maybe you didn't in your 2004 class, but if you're working with conservation of momentum, which is pretty much what we're doing in this class, we're kind of considering everything to be more or less static, so not moving, so energy and momentum is going to be conserved here. So with conservation of momentum, the derivation of this really is beyond the scope of what we talk about, but with conservation of momentum, the basic idea, and you probably talked about this briefly in your 2004 class, is that shear stresses that have subscripts ij will be equivalent to shear stresses that have subscripts ji. So for instance, tau xy is equal to tau yx, tau xz is equal to tau zx, etc., etc. Right? So in general, we can look at 9 states of stress, but only 6 of them are independent. And that's because we have this conservation of momentum sort of redundantly showing 3 states of stress. So generally, 6 independent states of stress. Okay. In rectangular coordinates, which is kind of what we're working with exclusively here, That's going to be sigma x. And we'll make this shorthand, and instead of writing the two x's, we'll just have one x. Sigma y, sigma z. In this class, we'll use as sort of the shear stresses tau xy, tau xz, and tau yz. Right. And we know that, flipping those scripts would give us redundant stress values. All right. Now, the 9 states of stress, 3 of which are redundant, usually get represented when we're talking about the 3-dimensional state of stress in a matrix form. Or more mathematically accurate, we would say that it's represented in what's called the stress tensor. Right? Have you guys talked about tensors ever before in any of your math classes? Nope. Okay. I'm not even going to touch that then. Let's just call it the stress matrix. Okay. So this is the basis for the stress, what's known as the tensor. This is the technically accurate name, or some people call it the stress matrix, which is not exactly accurate, but okay. And it would be represented as something like sigma ij is equal to a matrix that allows us to show all states of stress at one particular time. And it would have the normal stresses in the diagonal and the shear stresses in the triangular portions of the matrix. So this is a 3x3 containing like sigma xx, sigma y, and sigma z in the diagonal. And then the shear stress components are going to be along the triangles at the top. So this here is like tau xy, tau xz. Here we have tau yx, tau zx. Over here we have tau yz and tau zy. So this here is sort of the matrix that is commonly used to represent the full stress state at any particular point. So when someone is asking you, like, what's the full stress state, you could represent it using a matrix that looks like that, where maybe there's numbers filled in. Okay, 100 MPa for this value, 80 MPa for this value, so on and so forth. Okay, so you may see the full stress state represented in this 3-dimensional sort of manner. Okay, so this is sort of the basis for 3-dimensional representation of stress at any particular point. So you will see this formation again multiple times in this class, where I might give you a homework prompt that says the full state of stress at the point is bang. And I'm going to ask you, what's the principal stress? What's the maximum shear stress? Blah, 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 which we're going to get into and talk about in the lecture notes to come. So if you see me present a matrix like this, hopefully you understand that's the full state of stress. Now, this is what it's sort of represented in like a mathematical formation, but people have also used graphical representations of what's happening here. And to represent the full state of stress at a particular point, we would consider like the 3 orthogonal cuts that we made to be like 3 sides of a cube, okay? So you may represent visually as a cube, right? Where each side represents a cut plane. So what do I mean by that? Well, when we took our potato, we sort of showed 3 different images of that potato with 3 different slices through it in the 3 orthogonal directions. If we thought about taking those faces that we cut through and making a cube out of those faces, we could represent all the stress components on a singular cube by drawing it appropriately. So I'm going to do my best to make that cube here and give you a representation of what that might look like. Okay, give yourself some space on the paper to sort of draw this accurately. There's also a picture of this in the notes, okay? Okay, and let's have a coordinate system here that's sort of like running through the whole thing. Okay, that might be like X, Y, Z. And we're going to represent all of the stresses on this face based on like the cuts that we made to establish like the stresses on all of these faces, right? So sorry about that. All right. So this face here would represent like the cut that we made on the YZ plane. And similarly for like the top and this side, okay? And so let's draw the stresses that result on each one of those planes, and you'll see what is like this full three-dimensional stress state, or what is typically known as the stress cube. Okay, so we're going to have the normal stress coming off here, which is like sigma x x. We're going to have a shear stress on the x face in the y direction. So this is going to be like tau x y. And we're going to have a shear stress on the x face in the z direction, which is like tau x z. Similarly, on this face coming off here, we'll have like a sigma z z. We'll have a shear stress on the z face in the x direction. We'll have a shear stress on the z face in the y direction. On this face, we're going to have a stress coming off the normal direction, sigma yy. We'll have a shear stress on this face, which is like the shear stress on the y face in the z direction. And here we have a shear stress on the y face in the x direction. Okay. These are your 9 stress components. And the redundant ones would be ones that sort of pinch corners together. So like tau yz and tau zy are redundant. This tau zx and this tau xz are redundant, all right? This general picture is commonly called the stress cube. I think of my office as the stress cube, but this is the real stress cube. You have seen this idea before in 2004. And when you were in 2004, you generally talked about a two-dimensional state of stress. Usually in 2004, you represented a two-dimensional state of stress with like a single square that was basically looking on one particular face of this cube and neglecting all of the out-of-plane stress components. Okay? So I'll show you how this cube gets simplified to what you've normally seen in your 2004 class, and that is by assuming a state of like plane stress. Okay, so let's review plane stress quickly. So you should have talked about plane stress in 2004, but I'm going to sort of bring it home here for you just a second. So there are many situations in the world that exist where you can assume that what are quote unquote out of plane stress components are equal to 0. So I'll say many situations exist in which two faces of an element or of this stress cube are free of stresses. Okay, we would call this a state of plane stress. Okay. Typically, when you were working in 2004, you assumed that the z direction was stress-free, okay? Meaning you had no sort of stresses, either shear or normal stresses in the z direction, okay? So in 2004, I'll say ME 2004, you usually assumed, whether you knew it or not, that your sigma z was tau x z is tau y z is tau z x is tau z y is 0. Okay, sorry for all the little nonsense there. But those are assumptions that you usually made in 2004 to assume sort of a plane stress condition. And this would lead to sort of like a 2D state of stress. All right. So let's go back to our cube and draw what the cube would look like if all of these basically stress components were neglected and were set to 0. Stress cube. This is for plane stress. All right. So here we are. I'll sort of draw it a little bit more quickly. So if we assume that all these guys up here, sigma z, tau xz, tau yz, tau zx, tau zy are all equal to 0, then everything associated basically with this face here goes away. All right, so the normal stress on that face and the shear stresses associated with that face go to 0. The only stresses that you would see would be the stresses that are sort of on the kind of what would be like the xz plane and the yz plane. So you would see coming off of here a sigma yy. You would see coming off of here a sigma xx. Then you would see here your tau xy. And you would see here your tau yx. Okay. You would not have this component of shear, because for that component of shear to exist, you would have to have that component of shear. All right? So those guys do not exist because your tau zx is equal to 0. Okay? So those guys do not exist. Now remember to sort of like balance this out. You have to have these stresses on the opposite side to make things hunky-dory. So if you were thinking about like looking at the bottom of this cube or the back side of this cube, you would have similarly to balance on the negative y face and the negative y direction another sigma yy. You would have on the negative y face and the negative x direction sort of this guy looking here on the bottom side. And you'd also have on the negative x face and the negative y direction. Think about this sort of being on the back side of this cube here. Right? Tau sort of on the negative x face and the negative y direction. And also here is your tau on the negative y face and the negative x direction. If I was looking at this cube down the z-axis, I would just see a 2D square that had these stresses represented on them. So if you look down the z-axis, you would see this. There. That should look pretty familiar. Okay? You have probably worked almost exclusively with these two-dimensional elements. And I want you to understand that that is just one face of what would be like the three-dimensional cube that represents the full stress state of the material. Okay? Fortunately, like a lot of situations exist where this is all you really care about. Okay? Every surface of a material basically is in this condition, right? So it's very common to make this assumption on the surface of a material, right? So, I just wanted to sort of show you the three-dimensional state of stress and the analogy from 2004, which was like this 2D element that you have. Okay, so that's that. That kind of closes out sort of the introduction to this section. Now I want to get into sort of the meat of the discussion now, and that is talking about principal stress. And you probably talked about principal stress in 2D for your 2004 class, but I told you I was going to kind of rebuild this from the ground up because I'm, a little suspicious about your 2004 because in the spring it was, suspicious. All right. So let's just start with talking about what the principal stress is and how you might sort of like derive it or go about doing it in 2D, and then we'll move on to doing it in 3D. All right. The first thing that we have to do along that path is talk about stress transformations. And specifically, I'm going to start in 2D so that we're all kind of like hunky-dory and things are good. Okay. So let's assume that we have our 2D stress element in sort of like an XY plane, and we want to know, given some elemental stresses like sigma x, sigma y, tau xy, what the state of stress is in some alternate axis. So assume we have a 2D stress state at a point with known stresses sigma x, tau xy, and sigma y. Right? The picture that you should kind of have in your head is like this 2D stress element picture, okay, where you know like sigma x, sigma y, and your shear stress component is tau xy. I'll just label generally. All these shear stresses are more or less equivalent. Right? So that's the state that you should have in your head. And we could assume here that we have rectangular coordinates that are like x, y. All right. Now the point is that there are many situations where you are given a state of stress at a particular point in some coordinate system, but you're more interested in learning about the stress state in some other axis. This actually comes up on your lab, your combined loading lab. So you have a strain gauge on your lab that is aligned with some coordinate system that's not necessarily in your interest for doing analysis on the member. So if you remember from your sort of combined loading lab, and maybe I'll just have an aside here. Remember in your combined loading lab, you've got this bar. Guy walks into a bar. Just kidding. And you've got some point like on the side of the structure B, and there's a series of strain gauge rosettes that come off it looking something like that. All right, so along the axis of the bar and plus or minus 45. This has like an innate coordinate system associated with it that looks something like this. So let's just call it like the 1, 2 coordinate system. All right, but that coordinate system is not necessarily useful for doing analysis on this bar. Typically, if you're going to do analysis on the bar, you probably want to work in like a coordinate system that looks like this, where you have some axis along the bar and some axis upwards. So let's just call it like, cap x, cap y, or something equivalent, right? So I need to understand the stress at this particular point in the cap x, cap y coordinate system. But because of the measurements I've made in the lab, I might have the stress given to me in the 1, 2 coordinate system, all right? So if I want to, let's say, do my analysis in the cap x, cap y coordinate system and sync that up with something that I might know in like the 1, 2 coordinate system, I'll need to rotate from like the 1, 2 axes by, let's say, an angle here of 135 degrees to get to what would be like the cap x, cap y coordinate system. All right. So a lot of times students ask, like, what is the point of stress transformation? What's the point of strain transformation, etc.? This is why. Okay, maybe you have a known state of stress or known state of strain because of how you put your strain gauges on, and some coordinate system is not necessarily aligned with the coordinate system that is natural for the problem. Okay, so it can be useful to determine stress states in alternate coordinate systems so that you can like match them up. All right, so with that idea in mind, let's assume that there is another coordinate system that we're interested in having our stresses determined. And let's say that we want to have stresses in an alternate coordinate system. Okay, and let's call this alternate coordinate system, let's give the axes a name, and let's say that we want it in normal and tangential axes. Okay, and let's say that those normal and tangential axes are at some counterclockwise angle from the x, y axes. Oh boy, that y is a little squiggly. Which is the angle theta. So, we talk in English, but as engineers, we like pictures and we like symbols. So if we were to draw the other coordinate system here, it might be a coordinate system that looks like this n and this t, and it's going to be at an angle here, which is theta from x and y. Okay. All right. Now, if I wanted to determine the stress states, and I already knew what sigma x, sigma y, and tau xy was, well, maybe I just take the element that I have, and I cut along one of those n and t directions, and re-examine what the stress is along that cut side. So let's say I make a cut in this structure that's along like the t direction. All right, that might look something like this. All right, where I've sliced this particular guy, and it would be along an axis that is like the t-axis. Okay, so that slice through that guy is gonna be cut in such a way that this angle here is the angle theta. Okay, so that's what you would want to achieve and strive if you were looking to cut through this so that you made an element that would give you information about what's happening in like the normal direction. So after we do our cut, you're going to end up with what looks like a triangular element that looks like this. Okay? Where we still have like our x and our y directions, but now we have our associated n and t. Okay, and we might want to define some things here. We might say that this axis coming off here, obviously, is the n axis. And this axis kind of coming off here at the top is the t axis. And we're interested in the stress state on this particular face. So I want to know the stress on that face there. When I cut through this, I'm going to see a normal stress to that face, right? Which here is like this normal stress. And I'm also going to have a shearing stress on that face, which looks like tau n t, right? On the normal face in the tangential direction, tau n t. That has to be in balance with the stresses that are sort of already on the object on sort of the left-hand side and the bottom side, which I know. Okay, so I know that kind of on this back side here, I have a stress in the x direction. I know on the bottom side here, given to me, I have stress in the y direction. And I have on the sides here, what is tau x, y, equivalent for both particular sides. I'm just assuming tau xy and tau yx are the same. Okay. So the point is I want to come up with an expression for the normal stress in the new coordinate system and the shear stress in the new coordinate system that uses sigma x, sigma y, and tau xy. So I want an expression for sigma n and tau n t in terms of sigma x, sigma y, tau xy, and the rotation angle theta. Obviously, that's going to be an important piece of information. Now, how would one achieve this? Well, we sort of know that this structure with an assumption in this particular class is not moving, okay? And because our particular structure is not moving, the force equilibrium must hold. So think about your statics class, right? Some of the forces in all directions must be equal to 0. So to determine what the stresses are in like the n direction, we're going to write that stress in sort of terms of the force, which is like the force that would be required to achieve that stress divided by the area upon which that force is acting, which is the area of that length into the page. All right. So what we're going to do is we're going to sort of write these stresses in terms of the force and then use force equilibrium to write, let's say, sigma n in terms of the components of sigma x, tau xy, and sigma y that exist in sigma n. So to do this, we're going to enforce that the sum of the forces in the normal direction is equal to 0. This is static equilibrium. Okay, we will write stresses in terms of the forces which would cause that stress. All right. We'll also need some areas to help us along the way. Okay. So now to do this appropriately, let's define the geometry. We already sort of have like the stresses on there. Now let's talk about our geometry. All right. So for the geometry, I'm going to say that I want to make sure I'm very clear about this. This line here, we're going to assume is extended into the page. And it has an area of that length that you see on the paper into the page, which is dA. Okay? And that is the length of that line. Into the page, some unit thickness, whatever you want, T. Okay? That means that this face, if we have an angle here of theta, that means that this particular face here has got an area of dA times cosine theta. This particular area has dA sine theta. We all understand that? Okay. So now we're about ready for our force balance. Okay. So sum of the forces in N equal to 0. So the first force that I'm really going to see is maybe the force that's associated with this normal stress here. Okay. We'll recall that stress is equal to like force divided by area. That means that the force would be equal to like stress times area. Okay. So if I'm enforcing equilibrium here, I would say that my normal stress that's acting on this particular face here, multiplied by the area of that face, would give me the force in the n direction that would cause that sigma n. So sigma n times dA would give me a force. Right? And this is all entirely in like the positive n direction. So this here is like the force caused by N from sigma N. Okay, hopefully we sort of understand that. All right. That's got to be balanced out by whatever forces are generated from, let's say, sigma x, sigma y, and tau xy, right? Now let's take just a close look at what is this sigma x value, right? The arrow here is sort of like pointing kind of to the left, but we want to write the component of sigma xx in the n direction. So if we sort of thought about extending this n axis backwards here, we would see that this stress, sigma xx, is acting at this angle of theta. And so the component of sigma x that is along n is sigma xx times cosine theta. Right? Since it's generally pointing in the negative n direction, we would have minus, what is your sigma x times cosine theta, times the area upon which that stress is acting, which here is dA cosine theta. Okay? So this is like the amount of stress that's in n, and this here is the area upon which that stress acts. So stress times an area. And it's acting generally in the negative n direction. Similar idea for what's happening with sigma y. All right, except now we have sine components. So here's my sigma y, and this is acting at an angle of sine theta with regards to the n direction. So we have like sigma y sine theta, that is the amount of stress that's in n, multiplied over the area at which it acts, which here is dA sine theta. All right. I have to keep going. I'm not quite done yet. I still have contributions of tau xy here, which is sort of like acting at an angle of cosine theta, and this guy here, which is sort of acting at an angle of sine theta. Okay. So this here will be like minus tau xy sine theta times dA cosine theta. So this is the shear stress that is represented by this guy here. Minus tau yx or xy, however you like it, cosine theta dA sine theta. This all equals to 0. That's your force balance for this particular 2D element. Right? So assume tau xy equals tau yx and cancel the dA terms. They all are appearing there. So if we divide by dA, everything's just going to kind of go away. You're going to end up with sigma n is equal to, and I'm going to bring all these other terms to the right-hand side, make them positive. It would be sigma x cosine squared theta plus sigma y sine squared theta plus 2 tau x y cosine theta sine theta. And we have achieved what we set out to achieve. Okay? And that is writing the normal stress at some arbitrary new coordinate system, sigma n, in terms of the stresses that we already knew, sigma x, sigma y, tau xy, and the angle that n makes with the x-axis, which is the angle theta. All right, so that's where we'll stop today. we'll pick it up from here next time, and hope you guys have a good weekend.